Hello, those of you joining us. We're getting set up here and we'll get started in a few minutes. We got a little comfy couch up on the slides, and I hope you all are. I have myself a chamomile tea, getting comfy here this afternoon, and excited to experience this presentation together. So welcome, so glad you've joined us. I'm Kelly Jones. I'll be your sort of host today. And I use she, her pronouns. And if you all want to do us a favor, and as you're getting settled in, just pop your name, maybe a little bit of how you heard about our session today, and what you're hoping to learn in the chat. Because I'd love to sort of see who we got in the audience today. I think so it's Susan, because she's nodding.
Yeah, what we're going to talk about is a big field, and so knowing what you might be interested in might help us shape the conversation a little bit.
For sure. For sure. And everyone should feel free. You can turn on or off your video as you feel comfortable. We want this to be, I don't know, just a casual, good conversation today. And hopefully you've seen we're recording the session. We'll send that along with the slides that we show today to everybody who attends in case there are any links or interesting stats that Susan shares that you all are just curious to see later on. So know that that'll be happening. And yeah, we'll just hopefully have some folks introduce themselves in the chat and get to know each other a little bit here for a minute.
Don't be shy, step on up. What do you know? What don't you know? How come you're here? Any thoughts?
Well, here we go. People are getting settled in. We got Carl, sustainable engineering major. Susan as a former engineering major. That's a connection. Curious to know more about carbon capture at Michigan specifically, so that's great. A graduate student, Kaylin's joining us. Interested in learning more about carbon capture. Don't have a great understanding of what it entails. I'm hoping to learn more too, so we both have that one. Christy's here from Global CO2 Initiative. Yep. Cool.
Nice, very helpful.
All right. Well, feel free to continue entering in things into the chat. You can enter questions as we go along in there. Oh, Newt Nadelhofer, I remember you from previous events. Oh, Allie, senior in BBA. Nice. In the PJTL climate change program. Do you know what that
Thumbs
is,
up.
Susan?
Yes, I'll be talking about that.
Okay, great. That's
Nice to
awesome.
have someone from that cohort.
Cool. Excellent. Okay, well, folks can keep introducing themselves in the chat. This is very helpful for us as we're sort of tailing what we're sharing. Oh, hi, Caitlin. Glad you've joined us today, too.
And we know LS&A Facilities is a campus trailblazer in carbon management. So they worked on this so early. It's amazing.
So before we get too far into our conversation today, I always like to start our events with a land acknowledgement. Just because we're going to be talking about environmentalism and sustainability, and the indigenous peoples who lived here before colonization lovingly cared for this place we call Michigan, for many, many moons. So this is from the Native American Student Task Force. That's where this version of the land acknowledgement comes from. The University of Michigan is located on the territory of the Anishinaabe people. The Ann Arbor campus currently resides on land ceded to the Treaty of Detroit in 1807. Additionally, in 1817, the Ojibwe, Ottawa, and Potawatomi nations made the largest single land transfer to the University of Michigan ceded through the Treaty of Fort Meigs, with the hope that their children could be educated. We acknowledge the sovereignty of tribal lands and the painful history of genocide, forced assimilation, and displacement of Native communities that facilitated the establishment of the university. We affirm contemporary and ancestral Anishinaabe ties to this land, the profound contributions of Native Americans to this institution, and the university's commitment to educate the children of Native ancestors. The words on this slide won't undo any harm done, but they're a good reminder for all of our work to create a sustainable and just future, that we're doing that for all people. And if you don't happen to be joining us from Michigan today, I encourage you to check out native-land.ca. It's a great sort of crowdsourced resource of the different indigenous peoples and where they sort of originated. So that's what the map on the slide is from. So let's get into it and go to our next slide here. I'm going to introduce our speaker today. We're happy to have with us Susan Fancy. This is a picture of Susan from when she was a student here at the University of Michigan. And so I have her introduction here. Susan is the Associate Director of the Global CO2 Initiative. She assists with budgeting and financial planning, manages projects and processes at the intersection of carbon utilization research, commercialization, and education. And she leads student teams. As an undergraduate student in the College of Engineering, Susan was also the leader of the first solar car team in 1989-90, which you can see pictured here, which I think is pretty cool. I don't know if we have anyone from the current solar car team on the call. That would be fun, but maybe a little unlikely. But we're excited to have Susan here today giving us an introduction to carbon capture. Oh, that's for the end. I am going to actually stop sharing if I can find that button on my screen here. Hold on a second. Susan, great. All right, I'll let you take over.
Great. So thank you so much for that introduction. And yes, if you lead things and if you win, you may find yourself thrown into a mucky pond at the end of it at the finish line, which is what that picture was. So it's a pleasure to talk to you today about carbon capture and conversion, sometimes called carbon capture and utilization. And we will get underway with a poll. So Kelly, if you could
Folks should be able
tee
to see
that
it
up for
now.
us.
Yep, some answers were
So
coming in.
yeah, did you hear of it? When did you hear about it? I'd love to know. So we're seeing mostly positive. Well, that's good. That's encouraging. It's very encouraging. Some mixed, some
Maybe not
negative.
expected.
Yeah, yeah, I agree. Very,
Cool.
very interesting. Okay. Um,
Share our results there.
thank you.
Yeah.
Okay. All right. Let's move on to. So we're going to get started on our journey today with. It's having a little bit of trouble advancing. What's going on here? There we go. Just a little stuck. I would like for us to begin almost 200 years ago to look at the origins of where we are now. So here's what life was like in the late 1800s. And is that history refresher, the Industrial Revolution is generally credited to have started around 1860 and evolved through 1900. And the economy, the standard of living, the lifestyle, all was powered by fossil fuel. None of it was possible without the access to inexpensive energy. And did we have a carbon dioxide problem at that time? No, there was still transition then. The excess carbon problem that we're facing now began really with the Industrial Revolution. Before that, there just were not a lot of man-made sources of carbon emissions because we were focusing on animals and not cars to do a lot of manual labor. So what did that look like back then? A horse had a daily range of about 20 miles and put out about 40 pounds of solid waste. The modern equivalent of a car is that if you take an average of 20 miles per gallon, you're dropping about a pound per mile. So it's quite a bit. And the difference is that for us moderners, if we were to see that carbon dioxide, this is what it would look like. And one of the key things to note is that I think there was around 1 billion people on the planet, less than that, when this picture was taken. Now we have 8 billion. And it was called the Great Horse Manure Crisis of 1894. So our challenge with carbon dioxide as a waste is that we can't see it, we can't smell it, but it's very much there. So it's a challenge that we need to work on. Because of course, if we could see it, we would say, oh my gosh, that's totally unacceptable. I heard a statistic that if you were to gather all of the carbon dioxide humans have emitted into a band, it would form a band 14 inches thick around the entire planet. So, of course, that's not acceptable. Are we eliminating the horseless carriage? We're not. We like our standard of living. So that causes us then to look at the carbon cycle. What's going on with the carbon cycle on the planet? Earth has her own natural carbon cycle. If we remember from perhaps grade school, plants without a Canadian accent, plants suck up CO2, right? So they respirate it in for us, and then they store that CO2 as carbon in their tissues. And so at certain times of year, especially in warmer season, wherever you are on the planet, they're breathing in a lot of CO2. And then at other times of year, that CO2 is releasing through an exhale gesture with herbaceous plants. Trees, of course, will store it. They add woody material and they store it. So that's what we're seeing going on in the middle of this picture. On the left, we see human carbon emissions. You can see the power plant there, we see the car, we see the public transportation, and we don't see an equivalent down arrow yet of us pulling that carbon back in. The oceans have gobbled up a lot of our carbon, as has land itself. And we have the potential over on the right to remove some CO2. So that's what we're going to be talking about today. And how much? So this is a slide from the Center for Sustainable Systems at Seas. They put out a report every few years called Fact Sheets. And one American will ultimately need 3.02 million pounds of minerals, metals, and fuels in their lifetime. All of those pounds have a carbon emission associated with that. You've got to go get the material, move it around, transform it. These are just the materials themselves. It's not all the emissions associated with them. So it's kind of a staggering number. What happens for those carbon emissions affiliated with those products? First of all, where are they coming from if it's human? And where do they go? So on the left-hand side, we see sources. And we see the smokestacks there. And again, this could be an industrial plant. It could be the furnace in your house. It could be your car. It could be your lawnmower. It could be your chainsaw. It could be the electricity used to charge your cell phone. But those emissions are 89% where we're burning things to give ourselves energy. And then down below, where you see on the left, that picture of trees, cutting down forests is equivalent to emitting carbon dioxide because forests absorb carbon dioxide. So, and we're doing an enormous amount of deforestation still, especially, unfortunately, in the Amazon, which we desperately need to stop doing. So those numbers are 89% and 11%. Where is that CO2 been going? So if we turn our attention to the right, side of the screen. 41% of it's been going into the atmosphere. 33% has been going into the land. It could be going into trees, it could be going into soil, there's lots of sinks, could be going into minerals. And then 25% is going into the oceans. So you may have heard of oceans getting more acidic or getting more acid. Carbon dioxide, if you add it to a liquid or in general to materials, makes it more acidic. So that's been cause for things like coral reefs bleaching, species die off. And, there is concern, especially on the oceans front, about its ability to effectively continue to titrate our emissions. And we're not going to know until we get there. But we can't assume that that 25% can be 30% or 40% or 50%. So how do we deal with this? And as has been covered by Planet Blue really well, and they have great resources, there's lots of things we can do on a personal level and at the campus level. We need to get our emissions down, and we need to do it quickly. There are long lists available, but just as a brief refresher, things like those, energy efficiency measures, LED light bulbs, heating and cooling systems are usually big candidates, insulation, what we call electrification, which is where, if you are not currently on DTE's renewables program or their green natural gas program, that's a thought. You pay a little bit extra to help them pay to install greener sources of energy. Different choices, like don't take the car, buy less, especially things with packaging or things that come from faraway places like China. And in that case, you're supporting hopefully better social justice as well. Eat lower in the food chain, et cetera, et cetera. Plant trees. So today what we're going to focus on are that last item, H, which is capturing emissions in smokestacks so they don't reach the atmosphere, or direct air capture, which is the legacy emissions. And so we'll get into those details here. So what's really exciting is that if you look at the math, hopefully humanity will get their emissions down. But if you're not familiar with the current status, right now we are 9 months in to consecutive global record heat. 9 months hottest on record, row over row. And we are over 1.5 degrees C of warming right now. Now, hopefully that will go back down, and it should. Part of climate change is the temperature extremes, but so far, humans are not getting that curve bent down on emissions. So again, we desperately need to do that. Every single one of us has that responsibility. And we also can do things like plant trees or capture CO2. And what's really exciting about capturing CO2 is that you can turn it into products, things that you and I need every day. And there's two ways for us to think about this. We can turn that carbon dioxide into what we call circular carbon products. So things like soap or hand sanitizer or crayons or plastic, as well as commodity chemicals that are so important for industry. And those are things like ammonia or fertilizers for urea, pharmaceuticals. We can do this with captured CO2. So the way to think about that is all of those products, of course, degrade. And so that would be what we call circular carbon usage, where effectively you're capturing a CO2 molecule, you're using it, and then at some point you're going to reuse an equivalent molecule in the future to make the same product. But it moves us away from making these products from fossil, which is what happens today. So that's really, really exciting. So carbon capture can be one tool to give us access to products that allow us to have the standard of living that we appreciate. The other thing we can do with captured carbon dioxide is store it durably in products, and especially building materials. Concrete is second only in use to water in per capita global daily usage. Hard to get a figure on how much, but each of us effectively uses anywhere from 2,500 to 4,000 pounds of concrete per year. And that's a lot. And you can store a lot of carbon dioxide in those materials, as well as things like drywall, plastics, and carbon black products. So we've got a nice opportunity here in this brand new field. And so let's look at some terms before we take that apart further. What do we mean by this? One of the things being in this field that drives me absolutely nuts is people talk about decarbonizing. We are not decarbonizing. We are not changing organic chemistry. We are much more clumsy words. We're defossilizing, right? We're trying to transition away from fossil fuels, or we're de-emissionizing. The whole point is we don't want these emissions to reach our atmosphere and make the problem worse. But we are not decarbonizing in most cases because carbon is in everything, most everything. It may not be in high quantities. So as we look at this picture, for example, this lovely young woman eating a hamburger, she's 18.5% carbon. Her hamburger, kind of hard to get a bead on how much carbon's in there. There's something called embodied carbon, which refers to how much carbon it takes to produce something. And of course, the embodied carbon of beef is off the scales. I think it's like 18 kilograms or something of CO2 for one hamburger. But it's a lot, it's significant. And then, we can see she's drinking some bubbly, and that's got some CO2 in it. So carbon is only a problem when there's too much, but let's just be clear. We're not decarbonizing, we're defossilizing, we're de-emissionizing. And CO2 products that I'm talking about today are one part of the climate solution. And it's part of a suite of products that we need to embrace as a society. We need to adapt. We need to manage the impacts of climate change by, over time, moving away from coastlines and, getting more short sleeve shirts and all of those kinds of things. We need to be using a lot of renewables and other clean energy sources. We need to capture CO2 and store it, which I'll talk about in a minute, and then we can make products. And sometimes I hear in conversations that I'm participating in, what I hear is a drive for the best solution. There is no best solution. All of these solutions are highly imperfect. And if we're going to pull this off, we need to do all of them. And we need to do them rapidly, much more rapidly than we've ever done anything else as a society. And I think we're up for it. But, the Industrial Revolution took 40 years. We don't have 40 years to get this right. So thank goodness there's so much work going on in the field. So what is carbon capture and use? So when we talk about carbon management, what we mean is any efforts to reduce the current levels of carbon dioxide in the atmosphere. How many parts per million are we at right now? And there's two ways to do it. One, there's carbon capture and sequestration. We see that on the left. What we're looking at is a well. It's technically called a class 6 well. And these are usually at least a mile down, where carbon dioxide that you've captured is compressed into a liquid state and pumped down into that well, where it will bond eventually with the rocks. It starts out as a plume, it moves around, but it'll bond with the rocks. Minerals, especially magnesium and calcium containing minerals, naturally soak up CO2. You don't have to do anything for that to happen. It's like, just expose it and you're there. On the right-hand side, so we call that carbon capture and sequestration, or CCS. And we unfortunately are going to need CCS to make this emissions transition successfully. I personally am not excited about pumping things underground, but we just have too many emissions. And if you think about how quickly we're building out global renewables, which is as fast as we can, it's still, power companies have assets that they can't necessarily just rip up and replace tomorrow, just even from a labor point of view, right? I mean, we're installing wind and solar as fast as we can, but this takes time. So while we get that job done, we can capture the CO2 from especially those natural gas plants and stick it underground to help us make the transition. Is this a long-term strategy? No, this is not an enabler or a justification for long-term usage of fossil. It is a bridging strategy while we, get the rest of the problem better managed. And then the right-hand side is what we do at the Global CO2 Initiative. It's that carbon capture and utilization, again, where you capture the CO2 to make products. We unfortunately have been witnessing, especially in the last 6 or 8 months, the fossil industry. Carbon utilization used to mean what we think about, like, oh, let's use it to make ammonia, let's use it to make tennis shoes. And the fossil industry has glommed onto that and say we're doing carbon utilization, and not necessarily revealing that what they mean is that they want to use CO2 to, they're going to pump it under the ground to bring out more oil. No. So because of that, we actually are changing the terminology that we're using, which I'll get to in a minute. So let me just give you a visual for how this looks. So what we see on the left is an industrial plant. That's a cement plant. Actually, it's St. Mary's here in Michigan. And it is emitting carbon dioxide out of those smokestacks. So you again could put on carbon capture equipment, you could snag those emissions and then use them to make all of these products at their site, actually, ready mixed, concrete, precast, you could carbonate aggregates, repair mortar, and lots of other products. And on the right-hand side, what you see is what's called a direct air capture plant. And that's basically, it's sucking the CO2 right straight out of the air. It captures those legacy emissions. And to give you a sense for this, the concentration of CO2 in the air is 0.01%. In a smokestack, it's 10 to 20%. You got to work a heck of a lot harder to capture it out of the air. What that tells us is that, again, do the best we can to prevent those emissions from reaching the air, because it's a whole lot harder to get them out later. And it takes a lot more energy to get them out later. We can do it. And I do know, given Newt and one other person was curious about what we're doing about carbon capture at Michigan, I do know, especially Malcolm Bambling, he runs our Central Power Plant, and he's studying this stuff all the time. He would love for us to do carbon capture here at Michigan, and so would I. We're not there yet. I don't even know if we're able to think seriously about this yet, but we have the Central Power Plant, and then of course the North Campus Power Plant. And both of those are, especially the central one is bigger, is a decent candidate down the road for carbon capture. Something that people may not realize is that, especially the central power plant, although it does provide a lot of campus power, its primary mission in life is to provide steam. So I know we get upset that we're burning fossil fuels, but how are you going to get steam to all those operating rooms in the hospital if you shut down the CPP? That is not an easy question. And the energy associated with that would actually be a lot higher. So anyway, so there's just one thing about what's going on. This field in general is bleeding edge new. So I'm excited to see all of you here today to learn about it, because it's pretty cool. So here's what our United States Department of Energy might envision as a carbon capture ecosystem. So what we see on that back edge of this graph is sources of energy. We see geothermal, we see nuclear, we see solar, we see wind. These are low emission sources of energy. And then on the right-hand side there, we see some industrial plants. We see a plant making hydrogen. We see a cement plant, a steel plant, maybe a fossil fuel plant. And the idea with this is that all of those plants would be capturing their CO2 emissions out of their smokestacks. In the middle there, we see that direct air capture facility capturing CO2. And then we also see a biofuel energy producing CO2, as well as direct ocean capture there on the left and offshore wind farms. So, and you can see that there are these white, and then see those yellow lines, which are capturing the CO2 and then wanting to stick it all underground into that 1 mile down geologic storage there on the front. So this could be an ecosystem, and it is an ecosystem. We invented the word carbon capture, conversion, and co-location because we would like to see all of these things over time be close co-located. Why? Look at all those CO2 lines. Do we really want that stuff running across the countryside? Communities are not excited about this. There's safety issues, it's a lot more expensive, and it just makes more sense because so many of these loads are variable. Like when the energy is available, when the power plants or other plants are producing the CO2, when somebody, what's not represented in this particular vision is, all this, the companies that are making stuff with the CO2, which is what we get excited about. But you could coordinate the incoming CO2 and the demand if there was co-location. And so this is something we're really starting to advocate for. So how can we capture CO2? How is it helpful? First of all, let's think about 2074. In 2074, again, we are not changing organic chemistry. Where is all of the carbon that we're currently sourcing from fossil coming from? And I like to talk about Dow Chemical. So I was talking to Dow Chemical's head of research around 6 years ago. And I said, Yo, Keith, 70% of Dow Chemical's feedstocks are from fossil. What is Dow doing to replace those? Never forget what he said. He said, nothing. We don't think fossil carbon is going away. I thought, oops, and he managed to not react. It was very early days, and it's not his fault that he had that perspective. But 70% of Dow Chemical's feedstocks, I mean, Dow is huge, right? And so those are all those industrial chemicals. It's all of those plastics. It's all of those pharmaceuticals. It's all those fertilizers. All of that is fossil. If you go into a modern clothing store where most things are synthetic, that's all fossil. Plastic water bottles, laptops, all fossil. Cars, ton of fossil. So 50 years from now, we can't be doing that. So how does Dow Chemical and all other companies who need a source of carbon, which are currently getting from fossil, where's that going to come from? So it can come from, well, I'll work from the bottom up. It can come from what we're doing, gaseous or atmospheric carbon. You can capture that CO2 out of a smokestack or the air, and then combine it, if you need to, with some sustainably produced hydrogen and make hydrocarbons, which is what fossil fuels are. Fossil sources, they're hydrocarbons. You can do that. That's one really good option. You can recycle carbon, especially plastic, but also chemicals. Or you can use plant carbon, and take carbon out of a variety of land-based, woody and non-woody species, algae, things like that. That's it. Those are our options. And it is a little daunting to think about that because we're basically looking at where we started in this presentation. We need to reinvent the Industrial Revolution and the affiliated economy that goes with it. So how can carbon capture be done? You can take it out of the air. You can take it from smokestacks. Something we've touched on a little bit is you can take it out of water, especially the oceans. And if you remove CO2 from the oceans, again, they naturally absorb it because they're alkaline with all the minerals that are in oceans. If you take CO2 out of oceans, they will then reabsorb new CO2 from the atmosphere and effectively bring the levels down. So this is something that's really good to be doing. This is a field that just started to, I can't say it's exploding yet, but it just started to grow in 2023. It's brand new. There were you could know in one room the number of researchers working on this as of last year, but it's starting to really start to pick up, which is good. You can also do CO2 capture in freshwater, especially out of places where that water is already being moved around. So think wastewater or a power plant. And we actually have a team of students at the Global CO2 Initiative who are working on a project right now trying to build a demonstration for that. So if any of you students online are interested in some hands-on work, we will train, we need help as an independent study or as a volunteer. And then, of course, the plant and algae capture. One of the really interesting things about algae in particular is that they can make fuels for you. They can gobble CO2 and produce valuable chemicals. So moving forward here. So again, carbon capture and conversion is a holistic carbon management approach. It'll let us remove those legacy emissions. It'll help us harvest CO2 for our essential products and can replace that fossil carbon. So it's a really good thing for us to be doing. And in some cases, how long can it store that carbon? So going back to those building products, at least 100 years. And in the case of concrete, forever, or aggregates, forever. So it's a really, really fantastic option for us. Some plastics, same thing, things like carbon nanotubes, carbon black. And again, we need to plant trees. I hate picking favorites here, but when we plant trees, it's not forever. You know, it depends on the species, but you might get 200 years out of it. It just really depends. How well is it taken care of? So here's a list of all of the things that we can make from CO2. A little bit of an eye chart. Sorry about that. There's track 1 products store carbon durably. So construction materials, those carbon black type materials, and some plastics. And track 2 are those circular carbon examples. And what you see in that blue box is how big is the market opportunity? We've really been trying to push that to help companies see there's money here, folks. Because that's what, whether we like it or not, that's what still gets people moving. So what we see is a 1.1 to 4.4 trillion dollar market annually in 2050. To frame that, our current global market size is $86 trillion. So, and we can be gobbling up 2 to 27 gigatons of CO2. If you believe the IPCC and others, we need to be sequestering 4 to 10 gigatons of carbon through carbon capture at that time. Good news, we can do it. We've got lots of options. So second poll, what products would you want to buy that are made from captured CO2? Let's do a quick vote.
Let me get that
Athletic
pulled up
wear,
in
hand
one
sanitizer. Okay, athletic wear, hand sanitizer, a mattress, concrete blocks, and crayons. All of these are, the athletic wear is coming online, but the others are actually available today.
I think folks should be able to see it now.
Okay. Oh, interesting. Nice. Very nice. Okay. Give that another second. Yeah, so we get excited about the concrete, don't we? Because it ties it up permanently. But everybody, oh, nice. Everybody's excited about this. That's really good to see. Nice. Okay. That's good to see. Thank you, Kelly. Alrighty. So finishing up. Oops, doesn't want to let me advance. I've got to give that a minute. I did that last time. We are stuck in let me advance my slide, please mode. Uh, Okay, there we go. All right. So last leg here. What do we need to do to develop this new industry? There's a lot to consider, and I mean, the gift and the kind of the challenge with this industry is it's a lot harder than things like renewables or just using less because there's so much to consider. And you'll see this in the slides when they're distributed, but just a lot to think about. If you're going to capture CO2, for example, you probably don't want to be capturing CO2 and making ammonia if there's no ammonia market anywhere within 300 miles of where you think you want to capture that CO2. You have to think about things like that. Consumer acceptance, there's lots of assessments that need to go into this. Careful assessment to be sure that the environmental and climate benefits are real. And it's really easy to make mistakes on that source or to greenwash. Supply chain, like are the renewables there to power these processes, for example? You don't want to be capturing CO2 when you're running on a coal plant. No, that's not it. Where are the renewables to power it? And then also so many community considerations. What are the community benefits? What are the climate benefits, the environmental justice benefits, economic justice benefits to communities? So these are all things we need to think about. And there is a sweet spot. The dark green box there is those construction materials where we can get negative emissions. We can truly be removing CO2 from our atmosphere with a positive economic return. That underground storage, the light green box, there is permanent storage, but there's no economic return. One of the things we like about putting CO2 into products is there's a financial incentive to do so. Right now, storing CO2 underground is relying on a tax incentive that you and I are paying for. It's something called 45Q offered by the IRS. Again, we need to be doing it, but long term, that's not really how we want to be doing this. And then chemicals or agriculture, there's the potential for permanent storage, especially in agriculture with something called biochar, but enhanced oil recovery and some of these other areas, again, it can especially reduce demand on fossil, and that's important, but it's not necessarily going to solve the climate problem. So we just need to keep those things straight in our minds. I'd like to promote this game, and it's called CO2 Catch and Convert. We would be thrilled if you would play this. It's a game that lets you catch CO2 and then convert it into products. And you could play it and see if you can figure out how to fight climate change while also making money. And I'm embarrassed to say that I'm in this field and I flunked. Although I don't play, I've never played a video game before, so I have to I was struggling with that. But anyway, but others have played it and they've had a really, really good time. Um, here's a couple reasons to hope for the future. Why should we hope? Because right now, for carbon capture, there's very little that you and I can do right now today. We can't even run out and buy a product with a carbon label on it. There are some attempts at carbon labels that are similar to like USDA or organic, and to be honest, they're crap. Don't believe them. They're based on really poor quality carbon offsets. I don't recommend them. But we do have a lot of companies, and what you see here is a listing of the companies on the United Nations Race to Zero website. And I accessed this just a few days ago. I was really pleased to see that top line, 9,000 businesses. When I accessed it in June of 2023, that number was 6,316. That's how fast this is growing. And any company who has a carbon neutrality commitment has to be looking at carbon capture somehow. So all of these companies, investors, cities, and regions, and of course, I'm sure everyone is aware that University of Michigan has a carbon neutrality commitment. So does the city of Ann Arbor. City of Ann Arbor is not municipal. It is citywide for every resident. They're aiming for 2030. I think the most aggressive municipal goal that exists. Anyway, all these commitments cover 7% of our global CO2 emissions and over 15% of global GDP, and it's growing every day. So that's super exciting and a reason to be hopeful. Here is a really fun local example. This was from a couple years ago. This was a pour at Tri Delta for low carbon concrete. And this carbon, this pour had 38% less carbon emissions. And I'm also proud, just to put in a plug for us, that we helped write the guide for, supporting the city on why they should do this and those kinds of things. Also, just turning your attention locally to a study that, again, some fantastic students did. Again, if you're looking to work with us, we are always doing cool stuff with students. They did a study for a little nonprofit that is funded by the governors of 8 Midwestern United States states and then 2 Canadian provinces, premiers. This little nonprofit has a goal of supporting those heads of state with ideas for sustainable development. And they came to us and said, we think that climate and carbon offsets are very important for our future. How can our region be a go-to region for this? So the students studied that. And what you see there in that box on the left are forms of semi-durable or durable carbon storage. And forestation was included in that, as well as the aggregates, the precast concrete, and then that underground storage. And the lovely takeaway from this study was that there are not only enough sources for us to sink carbon in this region to balance out our own emissions, there's lots to sell for carbon offsets. So that was really nice. We offer a class in conjunction with the Center for Entrepreneurship called Perot Tech Lab. And Allie mentioned that. We are supporting startups in that space. We give them a team of 4 students for free for a year to solve any problem they have. And this is moving the needle. We are supporting the best startups in the world in this space. So if you want to join us on that at some point, let us know. And here is a list of things you can do. We've got a bog gardens exhibit. If you haven't seen Planet Blue's list of actions to reduce your emissions, totally check that out. It's easy to digest. You can look at the Carbon Almanac. You can study Project Drawdown. We have the Global CO2 Initiative Student Group, and they are working on those hands-on projects. I mentioned the one at wastewater. So, and you can work with us on independent studies and sometimes paid work as well. So right now, it's all about, reduce, reuse, recycle, and then these are other ways you can get involved. And last but not least, here is our vision. I didn't want to start with this because I thought your eyes may glaze over. Hopefully it now makes more sense, but we believe at the Global CO2 Initiative, the carbon dioxide capture and conversion is a mainstream carbon management solution and will become very important to a new economy going forward. And we do a lot with leadership, evaluation, teaching, research, etc. If you want to follow us on social media, we're very active on both Twitter, Instagram, and LinkedIn. And Christy will gladly send you our newsletter if you're interested in that. And at that point, I think I'll stop share and we can open it up for Q&A.
Yeah, thanks, Susan. That was helpful. I learned a lot in that presentation, and I know some folks have already entered in some questions into the chat. So I'll read those so we can have an easier time sifting through them a
Thank
little
you.
bit. The first one I love because it's just so optimistic. Carl asked, if we get to the point of having 0 carbon emissions from fossil fuels, is it possible to capture too much carbon that we need to stop doing it?
It's a really, really good question. And if you look at the land required to capture CO2, especially those legacy emissions through direct air capture, I don't think so, but it's a good question. It's a very, very good question. And the good news is that we do have enough land, if we're careful about how we plan food and housing, to install direct air capture facilities to help us with those legacy emissions.
And then we have another question here from Newt, talking about sort of the concrete production aspect of things. So concrete, making it produces a lot of carbon dioxide, yeah. Whereas existing concrete, especially if crushed, absorbs some CO2. That's great. So what's the net balance of the CO2 emissions like throughout the life cycle? So when you create the concrete and then when it sort of weathers at the end.
So another really great question. It okay, I want to be concise on this. So first of all, it depends on the product. If you have, those like concrete tubes that you see that like they use for like sewer pipe, they have a relatively thin wall section. And those wall sections, depending on what they're doing, can absorb CO2 on both sides. Something like that can absorb a heck of a lot more CO2 than a foundation slab, for example. So the form matters. And aggregates are usually at least 2/3. When I hear aggregates, I think rocks, think sand. 3/4 of concrete by mass is sand. Aggregates can absorb an enormous amount of carbon dioxide. If you just even run flue gas over them or purified, they can suck up a lot of CO2. Um, and you can cure with CO2. There are a lot of ways to do it. And what I like about your question, Newt, is that it's really important to understand the emissions that you spend in capturing or reducing those emissions and the net that's left over. And it's a really complicated answer that is case and site specific. I'm sorry to say, but there's a lot of opportunity there. So just in the interest of time, I think
Can I
I'll
respond?
sure. Yeah, yeah.
Uh, Thanks. That's a really good answer. Um, what surprised me was the IPCC reports and the US Global Change Research Program reports up until last year never mentioned, at least as far as I could tell, CO2 absorption into concrete. It was always listed as a source. And only the most recent one listed it as a potential sink. So
Agreed. And we also all look at horror in those same IPC reports where they show all the negative emissions as BECCS, right? Bioenergy with carbon capture and sequestration. I mean, that's not going to happen. So anyway, we can politicize about that. But yes, if we agree with that and yes.
thanks.
Yeah, that was a good one. Our other question here from Ai, sorry if I'm pronouncing your name wrong. Hopefully I got it close. It's why is CO2 pumped and stored into the ground as liquid and not as a gas, for instance?
Oh, that's a really great question. Um, it would take a lot more time and need a lot bigger pipes to try and pump it as a gas. So when you pump it, basically you're squishing it down. So like it's taking that fluffy sweater, putting it in a plastic bag, and then squeezing all the air out of it. That's my best analogy right now. You can tell I've been cleaning closets, but yeah, but you want to, and then you can get it down underground more easily, get it through the hole. So yeah, and do that economically.
Well, folks, if you have any other questions, enter them into the chat. I was just going to ask one about Susan, where do you see the jobs opening up in this space for the students that are on this call? If they're sort of, is it in industry? Is it in research? Like where do you see, I mean, there seems to be huge potential for this. Where would you direct them to think about for their future career?
It's a great question. There are opportunities in a lot of places. Yes, opportunities in research. Research is going to be going on for a very long time. There are companies trying to hire now. One urgent need right now is in life cycle assessment. You can't hire a life cycle assessment practitioner, and that's that. How do you assess the emissions from cradle to grave? You can't hire these people anywhere in the land. The Center for Sustainable Systems does some teaching on that. We're doing work we can teach by training. Policy is important. Just how do you make a product without using fossil? How do you do that? That's important. Um, how do you reduce the emissions in a building, those embodied carbon emissions? How do you do that? So, in architecture, there's so many opportunities. It's almost like look at a field and think about where the carbon management problems are is an easier way almost because they're on almost every field. Medical waste is awful. The carbon
Mhm.
emissions with medical waste.
Mhm.
Yeah.
Lots of opportunities. Maybe I should have taken that life cycle assessment class in undergrad back in the day. Um, cool. Well, I don't see any more questions in the chat, and I think I'm gonna head us to the wrap-up session, so we only have a couple more minutes here. Let me go ahead and pull up my slides again real quickly. Um, there's my second screen. Can you see them? Hopefully, yes.
Yes.
Great. So we've been trying to ask for feedback from folks for all of our Planet Blue Ambassador events that we have been having lately. So if you would do me the favor, and scan that QR code, or I'm putting the link into the chat right now. Go to that link, fill out that form, let us know, how did you hear about this event? What did you like about it? What did you learn? That will help us make future improvements on our events for our Planet Blue investors and friends here today. And then I can enter that into the follow-up email that I'll send you all with the slides and the recording. But I also wanted to share that next month is Earth Month, April, very exciting. And so our Planet Blue Ambassador program has two events that we're hosting. One is a tour of the M-City test facility. So if you're interested in any sort of autonomous vehicle testing or how that's all going, there's information on that. And we're also, at the end of the year, we tend to do a swag swap. So you've probably collected some swag that's Michigan branded. It might not all be your favorite. And if you want to come and trade it in Haven Hall with us on April 16th, that will be the forum. So you can pick up some swag you do want. But there's at least a dozen events happening as a part of Earth Month, including global CO2 emission initiative events at the Bot Gardens, etc. So check those out on the Earth Month website. I can put that link in the chat as well.
And just to extra pump that M-City test facility tour, there is some U of M designed flexible carbon sequestered concrete in the middle of M-City that's super cool, and you can see.
Amazing. I feel like there's a running trend. So our last event was at the Natural History Museum where we learned about cyanobacteria and how well they photosynthesize. You talked a little bit about that today, and then hopefully we'll talk a little bit about carbon capture at M-City. I love it. All right. Well, I'm going to stop sharing. Those are all my slides for today. Thank you all for joining us. Thank you, Susan, for presenting, and Global CO2 Initiative for providing your knowledge on this topic that I totally didn't have. If folks want to stick around for a minute, if they have a question, feel free. But otherwise, thank you for coming, and see you at a future event.